We have already discussed that the simple random sample is a really good, basic random sampling scheme, but is not sophisticated enough to handle other situations that we encounter on an everyday basis. With a simple random sample, because each sample of size n has the same chance of being selected, we can't obtain information for separate groups of individuals. For example, individuals of different gender, race, income class, religion, etc. Identify some separate groups we may want to hear from when asking the following question. Do you think our healthcare system works well? I'm sure you're coming up with all sorts of ideas in your mind about separate groups that we would want to make sure we heard from. Separate groups we would want to make sure are represented in our sample. For instance, those with health care and those without health care, those receiving Medicare, Medicaid, so insured, uninsured, employed, unemployed, sick versus healthy individuals, Medicare, Medicaid, pretty sure I just spelled that wrong, sorry, etc. So oftentimes we want to make sure we have separate groups represented. How do we handle this? A simple random sample doesn't guarantee all the groups we want represented are going to end up in our sample. We'll try the stratified random sample. The stratified random sample adds an extra step to the simple random sample. First, you divide your sampling frame into your distinct groups of individuals, which we're going to call strata. We choose the strata because we have an interest in the groups, or because the individuals within each group are similar and we want to account for the variability. So using these separate groups can account for variability introduced by having that group. So for example, graduate versus undergraduate students. After we divide our sampling frame into strata, we're going to take a separate simple random sample from each stratum. The best way to learn how to do a stratified random sample is to do an example. We have a club that has 25 student members and 10 faculty members. The club can send 4 students and 2 faculty members to a convention. We've gone ahead and stratified by students and faculty. You can see the separate table for students and the separate table for faculty. We've also given a line out of the table of random digits, line 116. This is going to help us take our stratified random sample. Now in practice, you could take your sample of faculty first and students second, or vice versa. In this class, so that we all get the same answer, we're going to do whatever group is shown first, and we're going to do whatever group is shown second, and we're going to go in order that way. Follow along with this example and hopefully that will become clear. Since students appear first, we're going to go ahead and take the sample of 4 students first. Notice that the students have 2-digit codes. So when we start reading in the table, we need to read off 2-digit codes. Our first 2-digit code is 14. So we choose Kim. Our second 2-digit code is 45, but this is above 25, which is our highest 2-digit code for our elements. So we're going to skip that one. 92 is skipped, 60 is skipped, 56, 31, 42, 48 are all above our range of codes, which only go up to 25. 03 is the next 2-digit code, so we choose Chen. 71 is above our range, 65. The next one is 10. 10 is Hostetler. 36 is outside the range, 22 is our next 2-digit code. And with this one we can stop because we were only supposed to get a sample of 4 students. Now it's time to pick our faculty. Notice the faculty only have single-digit codes. In order to get the same answers in this class, we're going to use the same strategy of where to start in the table of random digits. We're going to pick up at the spot where we left off from getting our sample from the first strata. So we're going to start with 5, 3, 5, 0, 4, 9, 0, etc. Since we have single digit codes, the next person that we pick is number 5, Lee, and then number 3, Fleigner. And this is how we get a stratified random sample using a table of random digits. Now, what do we do with a stratified random sample? Let's do another example. In an HIV study done in Houston, 921 heterosexual males were recruited. These individuals were known IV drug users who were not receiving treatment for their addiction. The individuals were stratified by race. Notice that we have 3 racial groups: Hispanic, white, and black. We have 107 subjects in the Hispanic group, 214 in the white group, and 600 in the black group. For each group, we have the number that were infected with HIV, and they've converted that to a percentage. So for the Hispanic group, the percentage is 3.74%. How did they get that? That would be 4 in that group that were infected divided by 107, and we'll call that p hat sub h for the Hispanic group, and that's how they got the 3.74%. So 6.54% was computed by taking 14 divided by 214, and 9.83% was computed by taking 59 divided by 600. We're going to use this information to compute approximate 95% confidence intervals for each stratum, using the quick formula for margin of error. So we get to compute 3 confidence intervals. The first thing that we need is the margin of error for each stratum. So I'm going to just put a little subscript on these as I work through them. I'm going to say MOE sub H for the Hispanic group. Our margin of error is 1 over the square root of n. And what's the sample size in the Hispanic group? The number of subjects is 107. So this is 1 divided by the square root of 107. There we go. And when you punch that into your calculator, that gives you 0.097, which is 9.7%. Now we're going to compute the margin of error for the group called white, and we'll give that a subscript of a w. Again, it's 1 over the square root of n. Our n here is 214. 1 divided by the square root of 214 is 0.0684. If you're wondering how I'm computing these so quickly, I did it before I recorded the video. So take your time when you're punching these in the calculator. And the MOE for the last group, we'll give that a subscript of a b. 1 divided by the square root of n. The sample size in that group is 600. 1 divided by the square root of 600 is 0.0408. And this comes out to be 4.08%. So now that we have the margin of error, and we've already got our p hats over in the percentage column, we can compute our confidence intervals. So the confidence interval is, for the first group here, 3.74, which is our p hat, minus our margin of error of 9.7, to 3.74 plus 9.7. And we'll give that p a little subscript of an h. When you take 3.74 minus 9.7 right here, what's the problem there? Well, you're taking a smaller number minus a bigger number, so you're getting a negative value, and we can't have a negative percent. So the way that we handle that is we just cap it at 0. So the proportion for Hispanics, we believe, is somewhere between 0 and 13.44%. That 13.44 is 3.74 plus 9.7. Doing a similar calculation for the white strata, our p hat there is 6.54. We're going to subtract our margin of error, which is is that 6.84 or 6.87? Looks like I meant to write 4 there. 6.54 minus 6.84. On up to 6.54 plus 6.84. And that gives us a confidence interval. Again, we'll cap it at 0 because we get a negative number for our lower bound. And our upper bound, 6.54 plus 6.84, ends up being 13.38. So we've got our first two confidence intervals. There's the first one. There's the second one. And now we're going to do our third one. Here, the confidence interval is 9.83, because that's the percent in the black group, minus our margin of error, which is 4.08. 9.83 plus 4.08. And that gives us 5.75 up to 13.91. So now we have our third confidence interval. So what can we tell here? Well, when you look at the p hats, we've got almost 4% of the Hispanics having HIV, almost 7% of the whites having HIV, and almost 10% of the blacks having HIV. Those look a lot different. When you're speaking of a disease like HIV, that seems like a pretty big difference to me, a pretty important difference. However, we understand these were each only one sample. And what do we know about samples? There's sampling variability. If we were to take other samples, those statistics might be a little bit different. So we have to account for that variability in our estimate. We did exactly that by computing confidence intervals. So now, when we account for that sampling variability that we know exists, what do we see? We see that the true proportion, the true rate of HIV might be the same for all three groups. These confidence intervals all share some values. Namely, from 5.75 up to the 13% range, they're all plausible values for any of those parameters, so there might not really be a difference at all. We say that these confidence intervals overlap because they share values. So, are there really true differences in the rate of HIV among the population proportions for the three groups? Maybe not. The confidence intervals share values. We say they overlap. When they share values, we say that they overlap with each other. So the population parameters might be the same. Later, we're going to say that there is not a statistically significant difference. there is not a statistically significant difference in the rates of HIV across the groups. Notice we didn't say there's definitely not a difference. We just said there's not a statistically significant difference. We're never 100% for sure of anything. Now, what if we want to lump the three racial groups together and get one combined estimate for the overall rate of HIV in heterosexual males? Well, we can pretend like this was all just one big simple random sample. And the way we do that is to take a weighted average of the sample proportions. So you figure out what percent of the sample were Hispanics. For instance, there are 107 Hispanics divided by the total number of people in the entire sample, which is 107 plus 214 plus 600. And if you punch that in your calculator, you discover that that's 0.12 or 12% of the sample. Do a similar calculation for whites and you'll discover it's 23% of the sample, and blacks comprise 65% of the sample. So the weighted average is the proportion for Hispanics, that's 12% of the sample, times the estimate for that sample, 3.74. The proportion of the sample that's whites, 0.23, times the estimate for that strata, 6.54, plus the proportion of blacks in the sample, times the estimate for that strata, and you get 8.34%. Watch out for this little phenomenon. There's a homework question on this. We've dealt with stratified sampling, talked about what it is, how to do it, and what to do with the estimates we get from it. Now we're going to talk about cluster sampling. In order to reduce costs in sampling, researchers focus on efficiency by sampling from clusters. Notice that cluster sampling focuses on efficiency. It focuses on saving money, saving resources. Clusters are often formed by geographic location, resulting in decreased travel costs for the research company. We randomly sample entire clusters, then survey everyone in the chosen cluster. We can use different combinations of cluster and stratified sampling to answer research questions about separate groups while still focusing on efficiency. Cluster sampling at first glance sounds an awful lot like stratifying, but they have different focuses. Cluster sampling is for focusing on efficiency, and stratifying is to make sure that you have separate groups represented and you can reduce variability. So let's try to picture cluster and stratified random sampling. Let's do stratified random sampling over here. And we'll do random cluster sampling here. Notice that I place the word random in a different location in each title here. Stratified random sample kind of enunciates and emphasizes the fact that you stratify first and then take a random sample from within each strata. In cluster sampling, however, the word random comes first. We're randomly choosing entire clusters. Hopefully that will help you remember what's going on. So let's say that these grids are each a city. And let's say that this city has 9 blocks. So we'll cut these grids into our city blocks. And on each block, there are exactly 4 houses. Way oversimplified, but hey, it's just so we can visualize what's happening. In stratified random sampling, we would call each of these blocks a strata. So this might be strata 1, strata 2, and so on. In stratified random sampling, we'd take a separate simple random sample from each of these strata. So we'd take N1 individuals from strata 1. So we might take one house from strata 1, N2 from strata 2, and so on. So we literally have every single strata represented, and we take a simple random sample inside each strata. In random cluster sampling, we divide into clusters, but this time we're focusing on efficiency. So we're going to sample whole clusters at a time. Here we have 9 clusters. Okay, from our picture. And we'll randomly select N clusters. Let's say N equals 2 for the sake of our example. Suppose cluster 2 and cluster 5 were randomly selected. Then all individuals in those clusters are in the sample. So in this case, if we randomly selected cluster 2 and cluster 5, then all 8 of those houses would be in our sample. So in stratified random sampling, we stratify and then get a random sample from within each strata. And in cluster sampling, we form the clusters and then we randomly select whole clusters at a time. So some of those clusters aren't represented.